Welcome to LIB Academy. This video is actually a summary of our previous video on description of periodic forces, where we also looked at momentum and energy operators, derivation. So we are going to make a quick revision on this. Those of you who were not able to watch that video might also get this useful. So we said periodic forces arising from, periodic motions arising from forces that occur in nature has attribute of wave described by classical equation as this. This wave equation also has a differential form to be this. Mind you, these are mathematical models that describe, trying to predict vibrations and wave-like motions such as periodic motions. And we said Schrodinger took as his starting point a fundamental equation for a wave traveling in the x direction for an electromagnetic wave traveling in a vacuum with a velocity c to be this. So Schrodinger actually started his equation from this electromagnetic wave. Classical wave. So this equation, classical wave and electromagnetic wave. Electromagnetic wave is actually a specific type of classical wave, right? So, and this classical wave and electromagnetic wave, they have the same formula structure. If you look at the mathematical equation describing electromagnetic wave, it do has either in the complex exponential form like this or in the differential form. They do have the same general formula. So Schrodinger replaced this y, which is the displacement of the wave in the x direction, with the wave function psi. Psi here. So because the electromagnetic wave and the classical wave, they do have the same general form, their general solution is also in the same form, like has the same structure. So Schrodinger replaced the displacement by y with psi as the wave function, where psi xt is a function that describes the behavior of an electron. The behavior of an electron, and is a function of distance x, the distance x and time t. So that is what we need to know. So the equation that we are much interested in is the general solution of this equation, the electromagnetic, which is written as this. Magnetic wave. I'm going to write this out. E to the power 2 pi I x all on, sorry, and then e to the power, this should actually be short, this is lambda, so here e to the power minus 2 pi I vt. So what we want to do here is to see how we can get momentum and energy operators. So our point of interest is this equation. The short form to write it is this, is like this. Alpha, where our alpha here equal 2 pi into bracket x over lambda minus vt. So if you replace alpha, the value of alpha here by this, and you expand the exponential, this is what you are going to get. And this equation, this function is known as the wave function, right? So what you have to know is this equation, the wave function, which is from the general solution of an electromagnetic wave. So this is the wave function. So you have to keep this in mind because we are actually going to get our equations, our other operators from this equation. So we are going to stand on this wave function and replace the value, the effect of Planck-Einstein's relation, and then in the Broglie's relation. Planck-Einstein relation is E equal hv. So let's make v the subject here. We are going to get v equal E over h, and the Broglie's relation is lambda equal h over px, where p is a moment, px is a momentum in x direction. It could be in the y direction or z direction when we are talking about other dimensions, right? Now we are looking at this in 1D, which is only the x direction. So what we want to do now is that we are going to replace, substitute the value of v here and the value of lambda there. Now let's try to work it somewhere and then substitute it in there. So this whole term, like the exponent, is 2 pi I x all on lambda. And we want to replace lambda by h over px. So this will give us 2 pi I x all divided by, okay, let's make it this way, divided by h over px. So divided by h over px. We want to, so this is equivalent to 2 pi ix multiplied by the reciprocal of this, which is px over h. And this should be giving us the whole of this divided by h. So 2 pi ix px all on h. So that is for where we substitute the value of lambda. Let's look at substituting the value of v there too. So let's take the whole term here, minus 2 pi ivt, And now we want to substitute v equal e over h there. V or equal e over h. So this is going to give us minus 2 pi I e over h, right? So e over h t. We can rewrite this whole term as 2 pi I e t all on h. So now let's adjust the exponent by these terms. So now this is what we are going to do. We now have our wave function xt equal c e to the power. After we substitute the term, the value of lambda there, what did we get? This is what we got. We are going to this exponent becomes minus 2 pi I e t. So instead of dividing this, like, okay, divided by h, which is the same. And this term right here, e, becomes this, right? So 2 pi I e t or h. So now we've adjusted the wave function. I said earlier that this equation, this mathematical model is called the wave function. So if you want to derive your momentum and the energy operator, just know the wave function, the general structure of the wave function. Then you start from there and then substituting the Einstein-Planck's constant, and then the Broglie's um, relation, which are these. From Einstein, you are substituting the value of v from there and the value of lambda from here. In here. So after that, you will get another relation, which is this, another equation. So what we are going to do now is to differentiate this with respect to time, and we are going to get something there. After that, we differentiate it with respect to distance, which is x. We also get something there. So now let's try doing that. We are now basing on this equation. We are continuing from there. So now let's differentiate this with respect to t. So d psi x t all over dt is will give us. So now these exponential terms, where do we have the t term? Actually, we are replacing v here, right? This is the lambda part and this is the v. When we substitute with v, we shouldn't be getting this term here. You see that it look at the same. So we should be getting 2 pi I x px. So 2 pi I x and px should be here. Okay. So we are differentiating with respect to t. So where do we have the term t? We have it here, right? Okay. So now differentiating this, if we are to differentiate dx e to the power u, is going to give us e to the power u multiplying by du over dx. It means we are going to multiply the whole term by the derivative of the power, right? So initially, we have to find the derivative of the power. So the derivative of the whole of this is going to give us what? Because we are differentiating with respect to t, Differentiating t is going to give us 1. So 1, let's say the power is 1 here. We multiply by that and the power will reduce by 1. So we get 1. So we are going to get a whole of this term over h without t. So 2 pi I e over h. Now we are done with the derivative, which is the derivative of the exponent, and then we now multiply a whole term by the exponent, which is e to the power minus 2 pi I e t over h, right? Then the rest of the terms, we don't have any t there to differentiate, so we are left with c here, and then e to the power 2 pi I xpx xpx all on h. So let's try rearranging this term here. We can rearrange this to be minus 2 pi I e all on h. Let's bring c first, followed by e to the power minus 2 pi I here e t on h. Then we bring this e to the power 2 pi I x p x all on h. So now comparing this to our wave function here, comparing this to our wave function right here, you could see that our psi x t equals c e to the power that we have c here, we have e to the power minus 2 something, we have e to the power here minus 2 a whole of this term, which is the same, and we also have e to the power 2 pi I xps over h. We also have it here, which is the same, which means that we can replace a whole of this term here by our wave function. Simply, we are going to write 2 minus 2 pi I e all on h psi x t, because a whole of this is the same as this here. Okay, so finally, if we differentiate the wave function with respect to x, this is what with respect to time t, this is what we get. Now let's arrange this in the eigenvalue equation form. How do we arrange this in the eigenvalue equation form? The eigenvalue equation is of the form this. Let's say assuming h operated on a function should give us, say, e and the function. So it means something operating on a function giving us a certain value plus that same function again, right? So we are going to arrange this whole term in that manner, making e as our main, trying to make e as our eigenvalue. So first of all, we can try multiplying a whole term by h, in which h will cancel here and we'll have a term of h here. So if we multiply both sides of the equation by h, this is what we get. This is what we get. Minus 2 pi I e all on, sorry, we've already multiplied through by h, so h is gone. We want to leave e alone here, so we just divide a whole term here by minus 2 pi I, leaving e, minus 2 pi I sorry, 2 pi I. Here minus 2 pi I. So minus 2 pi will take care of this minus 2 pi I. We are going to have a term here, a term of minus 2 pi I here. So this should be given as minus h over 2 pi I d over dt. Then since they are multiplying, you can decide to arrange them anyhow. Equal, we are only left with e here and the wave function. So you could see that we are getting something of this sort. So now let's stand on this equation. What is the main idea of eigenvalue equation? It means that if we have an operator acting on a function to give us a value in the same function, it means the value that we get is let me put it this way. If we have a momentum operator acting on a function, it will give us the momentum value in the function, the same function. So now we have an operator acting on a wave function to give us E. We said E should be our energy, right, from the Einstein-Planck relation and the function. So now it means that this whole thing here is the energy operator because it acted on the function, on the wave function, to give us the eigenvalue, which is energy here, and the wave function back. So finally, our energy operator equal minus h over 2 pi I d dt. So this is our energy operator. And this h here might be replaced by 2 pi. The relation between the reduced Planck constant and the Planck constant is this. So h can be replaced by h cross 2 pi. So in any way that you see it, you have to try recalling. You might not see it in terms of h, but in terms of the reduced Planck constant. So now we've differentiated the wave function after we introduce the Planck constant and the Broglie's relation into the wave function. We differentiate with respect to t, then we get our energy operator. Don't forget that. We differentiated with respect to t, and we now have our energy operator. We are going back to that same wave function to differentiate with respect to x and see what we get. we can just represent it by the wave function. All on h equal pi xt. So differentiating the wave function with respect to x, this is what you will get. Then now we are going to arrange this whole term in the eigenvalue equation form, trying to make px our eigenvalue. So first of all, we can multiply both sides by h to get rid of h. Then after that, we divide both sides by 2 pi I, remaining px and the wave function there. So if we multiply both sides by h will cancel h here, and then we have h term here. Two pi I px, the wave function x t. Now we want px to be our eigenvalue, so let's divide a whole thing by 2 pi I. Everything here by 2 pi I. Then 2 pi I will take care of 2 pi I. So at this place, we are going to have h over 2 pi I, the wave function, d over dx, the wave function, so will also be there, t, giving us px here, and the wave function xt. So now we have an operator acting on a function to give us momentum in the x direction, right? So this is basically a momentum operator. So this thing right here is a momentum operator, a linear momentum operator. So this is to tell you that if you have the wave function and you introduce the Planck and the Broglie constant into it, and then you differentiate the result with respect to t or time, you get the energy operator, right? The energy operator. But if you differentiate with respect to x, you get the momentum operator. So that's basically what you need to know. Differentiating the wave function after you introduce the Planck and the Broglie relation into it with respect to t, you get the energy operator, which is this, and with respect to x, you get the momentum operator. So that is it for this video. See you in my next episode.